A radio beacon has an operational range of 10 nautical miles. By what factor should the transmitter power be increased in order to achieve an operational range of 20 nautical miles? Should the by what factor should the transmitter power be increased in order to achieve a range of 20 nautical miles? So you can see over here that the original range was 10 nautical miles, and the new range that we want is 20 nautical So we want to double the range. Now, in order to double the range, you will have to you will have to increase power output by increase the power output by value of 4. Now, what happens is when a signal when a signal radio signal travels in the atmosphere, it undergoes or it suffers from attenuation. What is attenuation? It is nothing but loss of power or loss of strength of the signal. Okay. How far a signal can go, how far a signal can go, or the range of a signal depends on two factors. First, depends upon the rate of attenuation, how fast, how bad is attenuation. So it depends on that. And then second factor is it depends on the square root of the power output of the transmitter. So it depends on the rate of attenuation and it depends on the power output, the square root of the power output of the transmitter. So depending on the second factor, square root of the power output of the transmitter, if we want to increase the range by twice, okay, double it. So what will we have to do? We will have to increase the power output, which is square root of the power output. So we will have to square this by a value of 2. So 2 square is 4. So that's why in order to double the range, we will have to increase the power output by 2 square, okay, which is 4. So the correct option will be option number delta, which is 4. So you have to remember this fact for your exam. This question is often asked. Okay, so to double the range, increase the power output by 4. Let's go to question number 2. Night effect, which causes loss of signal and fading in bearing errors from NDB transmissions, is due to what? Is it due to skywave distortion? Is it due to interference from other transmitters? Is it due to static interference, or is it due to some solar phenomenon? So the correct answer is question 2A. Skywave distortion of the null position, which is maximum at dawn and dusk, meaning it will be maximum during sunset and sunrise. Now let's understand this. What happens is the non-directional beacon sends out omnidirectional signal. Okay. And the receivers on your aircraft, the automatic direction finding receivers, which is your sense aerial and loop aerial, what will they do? They will determine the direction from where this signal is coming, from where this signal is coming. And in so doing, they are able to determine relative bearing of the non-directional beacon from your aircraft. Okay, so the NDB transmits an omnidirectional signal. Automatic direction finding equipment in your aircraft will decide from or determine from where that signal is originating. And in so doing, it will be able to determine the relative bearing of your aircraft from the NDB station. The next thing, this NDB and ADF, they need a signal which travels in straight line. So to get accurate bearings of relative bearings, you need the signal to travel in straight line. In straight line. The next important thing is this NDB ADF works in the frequency band of low frequency and medium frequency. And the method of propagation, okay, the method of propagation is surface wave. So by following the surface of the earth, they go from the transmitter to the receiver. So the mode of propagation is surface wave. For VOR, it is phase wave, right? So for NDV ADF, it is a surface wave propagation. Now the night effect. Now originally what happens? Consider this is your earth, okay? And here is the transmitter. And in the atmosphere, in the ionospheric layer, there are two layers, D layer, E layer, F layer. Okay, so I'm drawing that. So there is a D layer, E layer, and then there is F1, F2 layers, right? So D, E, and F, this layer. So what happens is during the daytime, we have this D layer in the atmosphere. It is nothing but an ionized layer. And when the surface wave or when the NDB station sends out signals, the signal will travel the surface of the earth, surface wave propagation, and if any signal tends to go towards the ionosphere, this signal will be blocked or will be restricted going any further by this D layer, by this D layer. Okay, this way the signal will not be able to travel up into the ionosphere, and hence there will be no reflection from the ionosphere. Okay, so during daytime we don't have sky waves. During daytime, okay, during daytime, I'm writing it here. During daytime, we do not have sky waves because the D layer absorbs the surface wave coming at it. So remember this, during daytime we have the D layer, the delta layer, and it will block the wave to reach ionosphere. Okay. After reaching the ionosphere, hence get reflected back to the earth. So during daytime we do not have sky wave interfering with a surface wave. We have a normal surface wave happening, and this D layer is restricting or is preventing a skywave formation to interfere with a surface wave. But what happens during night time? Now during night time, this is your same surface of the earth. We have a transmitter here. Okay. Now during night time, we do not have D layer. Okay, the D layer disappears during night time. Hence, we are left with only E layer, F layer, so on and so forth. Okay. So what happens? The surface wave will originate from the transmitter. It will follow the surface of the earth, and any other surface wave which tends to go towards the ionosphere, it will go there. Okay. And after reaching the ionosphere, it will get reflected to the earth. It will get reflected to the earth. So this way we have many sky waves forming, and this sky waves will result in interference. Sky waves will result or interfere with the surface wave. So we have, I will label this. This is your sky wave. This is your surface wave. Okay. And this is what results in sky wave, sky wave interference. Okay, this all will result in skywave interference. So during night time, the D layer disappears. I am writing it here. During night time, D layer disappears. Hence, skywave will be reflected from the ionosphere and reach the earth. Okay. When this happens, one advantage is that the range. Sky wave, when a surface ray, in comparison with surface wave, the range given by sky wave is more. So the sky waves will cover other ranges than the surface waves. And one disadvantage is that the sky waves will interfere with surface wave. Okay, giving us inaccurate bearings. So this is one very big disadvantage of NDB, or a drawback, shortfall of non-directional beacon, that we have night effect. Okay, and this night effect is more pronounced during dawn, during the times of sunset and sunrise, dawn and dusk. uh, so the correct answer will be option number A. Skywave distortion of the null position, which is maximum at dawn and dusk. Now, the meaning of the null position, to understand that, we will have to know the principle of operation of NDB and area. So we will cover that uh, after, when that particular question related to the principle comes. So I will cover that topic there. So let's go to the next question, question number 3. Quadrantal errors, another important question, associated with aircraft automatic direction finder equipment, are caused by what reason? Okay, quadrantal errors. So now what happens? The basics remains the same. That NDB transmits an omnidirectional signal, right? Omnidirectional signal. And the automatic direction finding equipment in your aircraft receives this signal and determines direction is coming from. Hence, or this way, the relative bearing of NDB from your aircraft is known to you. Okay. Now, to determine this relative bearing, the signals must travel straight straight lines. Very important. The signals must travel in straight lines. Okay. So what happens when there is your aircraft? I will draw this aircraft. So let's consider this is your aircraft. Okay. So this is your aircraft. Now this aircraft metallic surface, the fuselage, it has electrical conductivity around its fore-axis and aft-axis. A strong electrical conductivity on its longitudinal axis, fore-aft axis. Okay. And so if non-directional beacon sends any signal which is aligned with this fore and aft axis, or which is perpendicular to this metallic surface like this or like this. So the error caused due to this quadrantal error is zero. Okay, if the NDB signal is aligned with the fore aft axis or is perpendicular to your aircraft, there is no quadrantal error produced. But if there is an NDB signal coming at any direction other than these four directions, we will have quadrantal error. Let's say this is your northerly direction, okay, and there is any signal which is coming at an angle of 45 degree, which is coming at an angle of 45 degree. This incoming signal will be bent. Okay, this electrical conductivity of aircraft will bend this signal in such a manner that it becomes aligned with the fore and aft axis of aircraft where the electrical conductivity is strong. So instead of coming like this at 45 degree, it will bend and try to get aligned with the fore and aft axis of aircraft. Okay, so originally it was coming from 45 degree, but due to this bending, the aircraft or the equipment ADF receivers on your aircraft will assume or will consider or will think that this signal is actually coming from any angle which is less than 45 degrees, which is less than 45 degrees. Okay, so your NDB station might be the real NDB station might be over here, but due to this bending of the signal, the aircraft might be forced to think that NDB station is not here, but somewhere in this line. Okay, and this is how inaccurate bearings are generated. Similarly, if there is any other signal coming at this angle, let's say 135 degree. Now, this signal will also be bent by the metallic surface of your aircraft in such a manner that it becomes as much as it is possible to becomes aligned with the fore and aft axis of your aircraft. So the result will be something like this. Okay, this bending will happen, and this will be tantamount to a signal coming from any direction which is more than 135. More than 135 degree. Similarly, if any signal is coming from a southwest quadrant, meaning it is coming from here, let's say a direction of 2 to 5 degree, so that signal will also be bent in order to align it with the fore and aft axis of aircraft. And this will be like a signal coming from any angle which is less than 225 degrees. If any signal is coming from this quadrant, let's say 3 to 0 degrees, so again that signal will be bent in order to align it with the fore and aft axis of aircraft where electrical conductivity is strong. So this is like a signal coming from an angle or from a direction which is more than 320 degrees. Okay. So this is your quadrantal error. Remember, you have to remember the points that I have written on this slide. That NDB transmits an omnidirectional signal. Your automatic direction finding a receiver equipment on aircraft will determine the relative bearing of this signal. Then all signals must travel in straight lines. Further, the metallic surface of your aircraft has strong electrical conductivity on its fore and aft axis. So if any signal is aligned with that axis, there won't be a horizontal error or any inaccurate bearing produced. But if any signal comes from any other quadrant, northeast, southeast, northwest, southwest, those signals will be bent in order to align them as much as possible with the fore and aft axis of aircraft, and this will definitely produce a bearing error. Inaccurate bearings will be produced. We call this quadrantal error because these are the quadrants. This quadrant will be called this quadrant will be called northeast quadrant. This quadrant will be called southeast quadrant, southwest, and northwest. So that's why it's a quadrantal error. So now the correct option here will be what? So quadrantal errors are skywave, ground wave, contamination. No, that is what we learned previously in night effect. Signal bending by aircraft metallic surfaces. Yes, so option B is the right one. Signal bending caused by electrical interference from wiring of aircraft. Wrong. This is where the concept of deviation happens. Magnetic direction, compass direction, and deviation is a result of that due to the electrical wires in your aircraft cockpit where the we get compass direction from magnetic direction. Option D is misalignment of the loop aerial, so that is irrelevant. So correct answer is option Bravo. So remember this, another important question. Let's go to the next question. Airplane is tracking away. Very important point here is to track away from NDB, maintaining track of 0 to 0 degrees, and drift is 5 degrees starboard drift. What should be the relative bearing of your aircraft? Now, first things first, relative bearing is equal to your magnetic bearing to the station minus your magnetic heading. Now, in this case, we have been given that track is 0 to 0 degrees, track is drift is 5 degree starboard. Drift is 5 degree starboard. Now with track and drift known to us, we can find out magnetic heading of aircraft. How? With a starboard drift heading is less than track, right? So if our drift is 5 degree, our track is 0 to 0, heading will be how much? It will be 0, 1, 5 degrees. Heading will be 0, 1, 5 degree. Heading will be less than your track. By what value? By a value of 5, the drift value. Okay. So heading will be 0, 1, 5 degree as given in the question. Now you're tracking away from the NDB. So this is your NDB station. This is your track 0 to 0. Now this track 0 to 0 is nothing but your QDR. Now this track 020 is taking you away from the NDB station. So the track that will take you towards the NDB station will be reverse track, which is opposite of 020, which is nothing but your 200, also called as QDM, right? Now let's draw aircraft. Aircraft heading is 015. So that means it is on track 020, but its longitudinal axis is pointing at 015. 5. 0, 1, 5. So heading is 0, 1, 5. Now, so your QDM is, I am drawing it here. Your QDM to the station is 0, 0. This is your QDR 020. Okay. Now, what is relative bearing? The definition is relative bearing is the angle between your aircraft heading. Is the angle between your aircraft heading and track to the station and track to the station. Okay. Next important point, this angle is measured clockwise from aircraft heading. This angle is measured clockwise from aircraft heading. So let's start. You have to start from here, the heading of your aircraft. Now we all know the difference. This difference between your track 020 and the track towards the NDB 200 is 180, right? The exact reciprocal. This is the exact reciprocal. So this angle is 180. Now to determine relative bearing, we have to start from aircraft heading. So our aircraft heading is here. So we will have to make an extra angle here. This and that angle, the difference, that angle is equal to 15 and 20, which is 5 degree. So we have to start from aircraft heading, count this 5 degree and another 180 degree. So our total angle will be 5 plus 180, which is 185 degree. So our relative bearing is 185 degree. This 5 degree and this 180 degree. Okay. So you have to start from your aircraft heading and then the track towards the LDB station. Okay. So total angle will be 185 degree. Or you can put the values here. What is the magnetic bearing to the station? It is 200. Magnetic heading is 015. So 200 minus 015 is 185 degree. So formula wise, this is the proof and diagrammatically it will be represented like this. So correct answer will be 185 degrees relative bearing. I have also solved questions of this type from RK Bali, uh, track and drift questions. So do watch those videos for more practice. Let's go to question 5. What is the wavelength of an NDB transmitting on 365 kilohertz? So frequency is 365 kilohertz. Make sure you convert this into hertz. So 365 into 10 raised to 3 hertz. What will be the velocity of a wave? 3 into 10 raised to 8 meter per second. And we should find out wavelength. Formula is V equals to frequency into wavelength. So wavelength will be velocity divided by frequency. 3 into 10 raised to 8 divided by 365 into 10 raised to 3. 365 into 10 raised to 3. So that is equal to 3 divided by 365, which is 8.219 into 10 raised to minus 3 into 10 raised to 5. So 10 raised to 3, 10 raised to 8, we are left with 10 raised to 5. Final answer will be 821.9 meters. So approximately 822 meters. So correct answer will be option C, 822 meters. It is very important that you pay attention to the units, meter, kilometer, nautical mile. Okay, and accordingly select the option. Over here, all the units are meters. So we need not convert the meter answer that we have found into any other unit. So accordingly, you have to find the answer depending on the options, what units they have used, what units they have used in the question. Bring all the units in confirmation with one another. Okay, all units should be SI units. That will make your calculation easy. Let's go to question 6. Which of the following is likely to have greatest effect on ADF accuracy? Interference from other NDBs, particularly at night, frequency drift at the ground station, interference from other NDBs at daytime, mutual interference between aircraft aerials. So the thing is, frequency at the ground station, this you can eliminate. Mutual interference between aircraft aerials, this option can also be eliminated. Now between option A and C, we have done this explanation previously. I have explained to you that NDB stations and ADF, the one error that we have is night effect. That is the error which is more pronounced at night time when we do not have D layer in the ionosphere. We do not have D layer in the ionosphere. That means any sky wave can go to the ionosphere, get reflected, and hence interfere with the surface wave. And that's how night effect errors are produced. Apart from that, there can be interference from other NDBs also. Like how? Now let's say there is an NDB station here. There is an NDB station here. Now when you're flying from one NDB station to another NDB station, there is something known as published protection published protection range. That means the maximum range the maximum range for which you can use one particular NDB. When you exceed that range or when you go beyond that range, maximum range, you will have to switch from the previous NDB to the next NDB. If you don't do that, you will get inaccurate bearings. How? There will be interference from these two NDB stations at your aircraft. So let's say the published protection range of this NDB is so much. For this NDB station, it is that much. So now when aircraft travels from one NDB protection range towards the other, it is important that when it enters the range, published range of this NDB, that it switches its frequency the next NDB station. If the aircraft or if the pilot doesn't do that, there will be interference. There will be interference from these two NDBs. Okay, so remember this. So first error is the interference from different transmitters, NDB transmitters. The second error is the night effect. What is night effect? I have explained that in the question 1 of this video. Okay, that when at night the D layer disappears from the ionosphere, the sky waves will return to the earth and interfere with the surface wave, which is the primary mode of propagation for NDB ADF system. So the correct option here will be option number A, interference from other NDBs, particularly at night. This interference will be aggravated during night time when we don't have D layer and hence interference from skyways. Okay, so let's go to question 7. There are two NDBs. One is 20 nautical mile inland, another is 50 miles inland from the coast. Assuming that the error caused by coastal refraction is the same for both propagations, the extent of the error will be maximum or will be more for what kind of NDB? One which is 20 nautical miles away from the coast or the one which is 50 nautical miles away. So what is coastal refraction error? The simple first basics. NDB signal, we all know, transmits an omnidirectional signal, and your ADF receiver in your aircraft will determine direction of this signal, that is the relative bearing of the station. Is the relative bearing of the station. Now all NDB signals travel in straight lines. Okay, so they have to travel in straight lines for ADF equipment to determine the direction they are coming from. What happens in case of coastal refraction? Let's say this is your land surface, and over here we have water surface. Okay, here there is water surface. There is an NDB station here. There is an NDB station here. Now, when this NDB station transmits a signal at an angle of incidence 90 degree, at an angle of incidence of, let's say, 90 degrees straight, okay, this signal will enter the water surface straight as it is. There will be no refraction. There will be no refraction. What is refraction? Refraction is nothing but the bending of a radio signal, radio signal when it travels from one medium to another medium. Okay, so that signal can bend. Let's say if this is a medium 1, this is your medium 2. There is a wave traveling from medium 1 to medium 2. So what will happen? That signal can bend like this or like this away from the normal. Instead of going straight through it, it will bend according to the refractive index of that material. So now if angle of incidence, next thing, what is angle of incidence? The angle at which this radio signal is traveling or meeting the coastline. Okay, if that angle is straight 90 degree, so there will be no refraction. But in case the NDB signals transmits this signal or radio wave at any other angle which is less than 90 degree, any angle less than 90 degree acute angle, there will be bending of this radio signal as it travels from land to water surface. Okay, so let's say there is another signal which the NDB has sent at an acute angle. After going to the coastline, it will be refracted. It will refract. Okay, instead of going straight like this, it will suffer refraction, and it will suffer refraction towards the coast. So I'm writing here, it suffers refraction towards the coast. It suffers refraction towards the coast. Okay, so this is your coastal bending error, right? Or coastal refraction, you can call it. So what happens due to this? If there is any aircraft, let's say there is an aircraft here, right? Now what aircraft does, it requires straight line radio signal. Okay, the radio signal must travel in straight lines. So instead of receiving this straight signal which it should have received, if there had not been any coastal bending error, it would have received this straight signal, and then it would have determined, that aircraft would have determined that the signal is coming from this NDB station directly. right? In that case, there would have been no error. The relative bearing generated would have been correct. But due to the bending of this signal over here, what happens is the aircraft thinks that this signal is traveling in a straight line. That means it has originated from a station which is not here but somewhere here. Okay, so that is what it thinks, that the signal, since it has traveled a straight line, that means the NDB station which it has originated from is somewhere here and not here. So this will result in inaccurate bearings. Okay, if there is an angle of incidence of 90 degrees, no refraction. Whatever the aircraft reception receives the signal, the NDB station will be the correct. The relative bearing will be the correct. But if there is bending of the signal, aircraft will think that it is coming from an NDB station which is not here but somewhere around that NDB station. And hence the relative bearing generated will be erroneous. So this is your coastal refraction error. Now this coastal refraction error can be minimized or can be eliminated, or you can correct that situation by using first an NDB station which is close to the coastline. So there may be two NDB stations. One is very close, one is over here, another is far away from the coastline over here. So between these two, you will use that station which is closer to the coastline. That will not give, or that will, not create a coastal bending error which is as great as the error produced by this station. The second solution will be, the second solution in this case would be to fly at higher altitudes. And then the third solution is that the angle of incidence is equal to 90 degree, at which there will be no bending error. So that is another possibility, angle of incidence to be 90 degree. So this is your coastal bending error in short. So the correct option here will be, there are two NDBs, one 20 nautical miles away and another 50 nautical miles away. So what is the solution I gave you here? Use the NDB station which is close to the coastline. It will give less error. It will give less error. So the question is, assuming that the error caused by coastal refraction is the same, the extent of the error plotted by aircraft that is over water will be what? So the error will be same from both beacons when aircraft is on a relative bearing of 180 and 360 wrong. The error will be greater for the beacon which is 20 nautical miles inland. That is also wrong. The error will be the same from both beacons when aircraft is on a relative bearing of 090 and 270. That is also wrong. The error will be greater for the beacon which is 50 nautical miles inland. So this will be right. Okay, error will be greater for any station which is farther from the coast. Let's go to question number 8. Errors caused by the effect of coastal refraction on bearings at lower altitudes are maximum when the NDB is inland and the bearing crosses the coast at an acute angle. Yes, maybe. Let's check the next options. When the NDB is near the coast, no. So the errors are maximum. So when NDB station is near the coast, error will be minimum. So B is eliminated. Charlie is when the NDB station is inland, that is very much away from the coastline, and the bearing crosses the coast at right angle. So this option will also be wrong, because when the signal is at right angle, the error will be minimum. Delta near the coast. So delta will also be eliminated, because whenever an NDB station is near the coast, we won't have this coastal, or we will have an error which is minimum. So we are left with option A, which states that NDB is inland, very far away from the coast, and the bearing also crosses at an acute angle. Let's go to question 9. An airplane is tracking towards an NDB. So the important words here are tracking towards. Maintaining track 120 degrees with 15 degrees starboard drift. What is the relative bearing? So same, relative bearing equals to magnetic bearing to the station minus magnetic heading. Now here we have that our track towards the station, it's given in the question, our track towards nothing but your magnetic bearing to the station is 120 degrees. Next, we have been given that drift is what drift? It is 15 degrees starboard drift. Whenever we have starboard drift, we will have heading less than track. So if track is 120 and drift is 15 degree, so our heading will be less than track. So 120 minus 15, which is equal to 105 degrees. 105 degrees. So let's substitute the values. Magnetic bearing to the station is what? 120. Magnetic heading is 105. So answer will be 120 minus 105, 15 degree. So relative bearing will be 15 degree or 15 degrees. So Charlie will be the correct option. Let's go to question number 10. Diagram wise, if I have to draw this, let's say this is your NDB station. Okay, and the track towards that station is 120. So okay, track towards that station is 120. Aircraft heading is 105. 105 degree. And now, what is the definition of relative bearing? It is the angle between your aircraft heading and the track towards the station. So this is your heading of aircraft being, and this is your track towards the station. So the angle between them should be measured from the heading clockwise. So this angle. So this angle is nothing but 120 minus 105, which is 15 degrees, which is 15 degrees. Okay. Next, what is the wavelength of an NDB transmitting on a frequency of 375 kilohertz? So wavelength will be equal to velocity of wave divided by frequency. Velocity is 3 into 10 raised to 8 meter per second. Frequency is 375 kilohertz. Convert that into hertz. So into 10 raised to 3. So 10 raised to 5 multiplied by 3 divided by 375, which is 8 into 10 raised to minus 3. So wavelength will be equal to 8 into 10 raised to 2 meters. Also 800 meters. So option Bravo will be the correct option. Option Bravo will be the correct option. With this question, we have come to the end of this lecture. I hope you have understood all the 10 questions, the solutions, the explanations, the concept behind every solution. If you have any doubt, questions, you can ask me in the comment box. And if you have liked this lecture, hit the like button, subscribe to this channel and share this video with your friends. All the best. I'll see you in the next video.